He's a software engineer and a team lead with 10 years of experience with Java, and he'll talk about CQRS and Axon. So please, there you go.
Okay, hello everybody. We have just said my first slide. So,
not all of it.
Okay. Okay, yes, well, Cross is a company where I work. Basically, most of the time today I spend as in various technical roles and organizational roles on the projects that we have. First, I would like to talk a little bit about how do we develop software today. Most of the applications that we see around today are built around some kind of a layered architecture, like this, for example. And many of them are built also as monoliths. And there is nothing wrong with that. Layered monoliths are fine. They serve their purpose, at least for some time. So, in the beginning, our application and our domain models are relatively simple. There are clear boundaries, and every component has its place in the big picture. But as time goes by and new features get introduced, our model gets complicated and our application gets complicated. So, since many of the new features weren't planned at the beginning, our model wasn't designed to support them. So, eventually, after a period of time, our application and our model turns into something like this. So, to deal with the problem, we try to split the different parts and perhaps separate our application into several applications or microservices. But we soon find out that everything is so interconnected, and basically it is impossible to do it. So, perhaps we should try something else instead. The first concept I would like to talk about today is called event sourcing. And it is a little bit overloaded term today, so frequently used in different contexts. So let me first explain what do we mean when we talk about event sourcing. For starters, event sourcing is not the same as event logging. Many systems today log some kind of events, but they do it in a way that event log is just a thing that sits aside to a core domain model, like a file or a data or a table, for example. The main characteristic of event sort system is in the way how it handles the current state. In classical architectures, like the layered architecture that I have just shown, current state is persisted in some kind of persistent storage, like a database or something like that. Event sort system doesn't store any of the current state. Instead, it derives it from the events that have happened in the past. So instead of storing the current state, it stores the facts that have led to that state. That means that all of our current state is basically disposable, since we can always regenerate it from the events we have stored. And we can think of the current state as some sort of a cache, or as a result of the equation. Many businesses today are event sourced in its nature. If we take banking, for example, the current balance of our bank account is certainly important, but what led to that balance amount is something that is important, perhaps even more. So, if we store all the facts that have led to our current balance amount, then perhaps the amount itself could be transient. And we could always calculate it by summing up our deposits and withdrawals, for example. So, what are the events? When modeling a business domain, we can think of events as things or business facts that have happened and that are of some kind of interest to us. So, business facts that have no importance for our business case are not considered to be events. since they are since they describe something that has already happened, they are always expressed in past tense. For example, in banking domain, we could have events like account opened, funds deposited, funds withdrawn, money transferred, account statement issued, etc. In e-commerce domain, we could have events like item added to cart, item removed from cart, order placed, payment received, and goods dispatched. So, a single event itself should completely describe a business fact. So we say that events are completely self-described. However, it is important to note that they are not denormalized. And that means that a single event should contain only the data that is of interest to a particular business fact that it is trying to describe. All other data should be held as a reference only and accessed as a reference. In event sourcing, events represent the center of the entire system, so modeling them well is crucial to our success. If we consider our e-commerce example, we could model it to persist a current state in some kind of relational database and perhaps end up with a model like this. We could have an order table that has relationship to order items table, shipping others table, or payment table. But we could also model the same business facts like this, as a single ordered stream of events that follow the user interaction with our application. And we could persist them like this. We call the persistence mechanism for persisting events event storage, event store. So one of the important characteristics of the event store is that the events should be stored in the same order as they appear in our system. So event sourcing is just another way of storing information. Or perhaps there is more to it. From what I've said so far, we can conclude that in event source system, the data is append only. And that is because you cannot delete the events that have already happened. We can also conclude that the data is immutable. And that is because you cannot change the events that have already happened. So, a natural question arises is, how do we deal with mistakes? Well, the same as in real life, with correction events. If we look at the following two streams of events, for example, we can easily see that they will lead to the same current state. But if we design our model to persist the current state only, then aren't we losing something? If a customer comes to us and asks us to give him a report of all the items users are removing from the carts, so perhaps they could offer them those same items at a lesser price, we wouldn't be able to do that. So if your system has two different use cases that end up in the same current state, then you are probably losing data. Apps age like fish, data ages like wine. Since we cannot predict the future value of our data, we cannot afford to lose any of it. And event sourcing concept enables us just that, never to lose any of our data. One of the benefits of the event sourcing is that systems like that are deterministic. That means that you can always go back to a point in history, reload all of your events to that specific point, and put your whole system into the state as it was at that precise time. It's something that is useful for troubleshooting and various inspections in your system. So, another concept that event sourcing goes really nice with is called CQRS, or Command Query Responsibility Segregation. It's perfectly possible to use one concept without the other. It's just that the real power of both concepts comes into play when you use them together. So, let's first see how reading of data works in this kind of combined architecture. Let's say that we have our client and our event store. We don't want clients to read directly from the event store. And that is because clients usually want to read some kind of current state. And since our event store isn't designed to persist the current state, we need something else. And we call that something a query handler. Query handler is responsible for querying data from some kind of data representation and returning it to the client. We call that data representation a projection. Projection, on the other side, are built using an asynchronous process that we called projector. So projections are basically some kind of current state representations, and projector is following the event store and using the events from the event store to build that projection. Important thing here is that the projector himself is responsible for tracking event store and not the event store. So every projector will have its internal pointer to the index in the event store so he could know where he has left off. And this enables us to have as many projections and projectors as we want, since they are completely decoupled from each other. We can even use different persistence mechanisms for our different projections. And so instead of having a single relational model that is optimized for reading and writing, we can have as many models as we want that are optimized for reading only. And this is something that is really powerful with CQRS. Projections are cheap. That means they can easily be rebuilt. Just reset their pointer to 0, let them catch up with the event store, rebuild, and when they are done, switch to the new one and throw the old one away. So, before discussing how writing of data in this kind of system works, we need to explain two more terms. And first of them is commands. Same as with reading, we don't want our clients to be able to write directly to the event store also. Instead of that, clients should express their intentions with something that we call commands. So, since commands express only the client's intention, that means they can be rejected. Unlike events, which represent the facts that have already happened, so they cannot be rejected. If commands are accepted, then they result in new events. We said before that events represent something that has happened and that they are expressed in past tense. Commands represent intention and they are always expressed in imperative. In our banking example, we could have open account command that will result in account opened event, deposit funds command that will result in funds deposited event, withdraw funds, funds withdrawn, transfer funds, funds transferred, issue account statement issued. Another term that we need to discuss is called aggregates. So events happen to something, and we call that something an aggregate. It is a domain-driven design term, and in our domain modeling language, aggregates are nouns. important characteristics of aggregates are that they contain logic, they all have unique identifiers, and they often have some kind of life cycle. Aggregates can also refer to each other through references. So, in our banking example, we could model our domain like this. We could have events, account opened, funds deposited, funds withdrawn, happening to something that we call an account. We could have funds transferred event happening to an aggregate that we call transfer, and account statement issued event happening to an aggregate that we call account statement. Okay, let's see how writing of data works. So we have our client and we have our event store. And as we said, we don't want our clients to write directly to the event store. This would be like opening a database to your browser, for example. And it's not something that you want to do, since you will probably want to validate the data that comes from the client before you store it. So the client will issue a command, and command will be picked up by a component that is called command handler. That will trigger loading of all events from the event store that are tied to that specific aggregate. So every command should always have aggregate identifier, so the system would know on which aggregate it is referring to. In the next step, command handler will instantiate. Okay, so pictures is not seeing correctly. Okay, we'll instantiate new aggregate and replay all the events on the aggregate itself. So basically, it will rebuild the current state of the aggregate. When this is done, aggregate will take a command and decide what to do with it. If the command isn't accepted, then nothing will happen. Perhaps an exception will be thrown or something like that. And if the command is accepted, it will result in some new events. So, isn't this slow? It certainly can be. Domain modeling is not easy, and this concept doesn't change that. So some things to watch out for are try to keep the number of events per aggregate as low as you can. Also, try to keep your events as small as you can, so they would quickly be persistent and retrieved from the event store. Except having long-living aggregates, try to have fixed life aggregates. There is also an optimization called snapshots. Basically, it is a concept where you periodically record the state of your aggregates in the event store. So the reloading of aggregates doesn't always have to go from the beginning. But instead, it can process only events that have happened after the snapshot was taken. This is a purely technical optimization, and basically it has no role in the concept itself. So, if you look at our architecture once more, we said that we have our client. Client will express their intentions with commands. Commands will be picked up by command handlers. Aggregates will do something. It will probably result in publishing new events to the event store. We have our projector, asynchronous projector that is tracking the event store and building up a projection. So when the client queries some information, query handler will take that query and load the data from some projection. So, to conclude, this kind of concept enables us to have completely separated models for reading and writing. And because of that, we can scale both sides independently. So in this architecture, writes are fast and consistent, but the reads are also fast and are eventually consistent. And that is something you should be aware of. So both of these concepts are not new. They have been around for quite a while, but they haven't been part of the mainstream. So if you like, you can implement all these components by yourself, or perhaps you can use a framework. With framework, you'll get all the scaffolding and the components, so you can spend more time on your domain design or something like that. So a framework that we are using is called Axon framework. It is an open source, Apache licensed Java framework. There is also commercial support for it by Axonic company. Axon provides all of these components out of the box. It has very nice Spring support, but it doesn't require you to use Spring with it. So you can configure everything in Axon programmatically, and you don't need to have Spring in your class path. It's just that with Spring, configuring is much easier because of Spring's annotation support and Spring Boot's auto-configuration support. So the architecture of the Axon framework looks like this. It seems complicated, but it really isn't. Basically, those are all the components that I have just talked about. So the read side is completely separated from the write side. On the right side, we have our domain model components, our events, commands, and aggregates. We have a command handler component. A command handler is using a repository for interaction with event store. And we also have a new component that is called command bus. Basically, command bus is responsible for routing commands to the proper command handler. On the read side, we have query bus and query handler. Those concepts are new in Axon. They are available only from the latest version of the framework, so we are still not using those. There are projections as a component, and there is a component that is called event handler. Event handlers are used to implement projectors. So there is also another hidden component in Axon that is called event processor. Event processor is basically tracking the event store and calling the event handler. So event handler and event processor are like a projector on our last image. In Axon, there are two possible event processors you can configure. You can use a synchronous processor that is called subscribing event processor, or you can use asynchronous event processor that is called tracking event processor. Other components in Axon are event store. Axon provides out-of-the-box relational database as event store or a Mongo database. They also have their commercial version of event store also. In Axon there is also a concept of sagas. Sagas basically represent kind of event handlers that are used to publish new commands instead of building projections. So, how do we implement things? Clients use command gateway, they call send method, which returns completable future and completes only after the whole command is processed. We annotate, command handlers are implemented by annotating methods with command handler annotation and by putting commands into parameter definition. They are used for logic implementation. They inspect the state of the aggregate, but they shouldn't change it. Event sourcing handler methods are used for that. They are used for invoked when during the process of rebuilding the aggregate state. And on the read side, we have event handler methods that are used for implementing projection generation. So, how you can implement application with Axon? You can start with Spring Boot initializer, for example. There isn't any support for Axon yet, so you need to add the dependency manually. First thing you would like to do is you need to define your domain model, so you need to implement your commands, events, and some initial version of aggregate. Important thing here is that fields that are used for aggregate identifiers in commands should be annotated with target aggregate identifier. So in Axon, everything around aggregates is expressed in terms of commands and events. So we can have a simple test fixtures that are implemented only using those terms, and that they are completely implementation independent. So after defining our domain model, we can write a test that basically says, if we are given some set of events, when I apply this command, I expect these events to happen. Here we are using Spock and the Groovy. Axon puts all the command handling logic into the aggregate itself. It uses constructor for implementing command handlers that create aggregates, and plain methods for implementing all other command handling logic. So the command handler methods are basically divided into two parts. The first part takes the current state of the aggregate, takes the command, and makes some kind of decision. The other part applies new events based on that decision-making logic. So the command handlers only inspect state and never change it. The changes of the aggregate state go into the event sourcing handler methods. Basically, those are the event handlers that get invoked during the process of rebuilding the aggregate state. So, why is these two things separated? It is because you don't want to have any logic when you apply the events that have already happened. You just update the state. On the query side, we can have simple Spring component beans and methods annotated with event handler. Those methods will be invoked when event processor of Axon finds an event of that type in event store, and they can be used to implement some kind of relational projection, like with our JPA repository here. So, some of the things we have learned so far. Using this kind of concept is not easy. A significant amount of time is used for domain modeling, and basically the good approach would be to start simple and add complexity as it becomes needed. So if you have an application that is like 300 fields form and a single save button, that perhaps this is not the case for you. So this kind of architecture requires a task-oriented UI, so you can model your commands and events nicely. Eventual consistency is introduced with asynchronous event processing, and that is something to be aware of. Also, core domain model shouldn't change a lot, but in real life, I think that is virtually impossible to avoid, so you will eventually need some kind of event versioning. So, okay, I understood. So, okay, we are out of time, so I don't know if there's time for questions. Okay. Okay, I can answer your questions. Just